Alright, welcome to another draft physics video presentation. Some more on photons, the double slit experiment again. Why not? I've been over it. But with each video there's more and more refinement, and becomes more and more obvious that they have the wrong answer, and there are simpler, better answers to what's happening in these experiments. Kind of that simple.
Welcome to Lecture Online, and here's the very specific case of light interference. All
right, so the idea is the light really isn't interfering, and you have a couple of reasons not to believe it does this interference thing, in the sense that you can't shoot light into light and have it interfere with itself. It just doesn't happen, and the theory just doesn't make any sense, because you really can't cause this thing to, there's just no mechanism, no description of a mechanism. And so the idea is that somehow a slit or some other obstacle, a pin, a needle, anything you stick in front of the light, that somehow this fundamentally changes photons into some other thing, and that somehow this other thing can interfere with itself. Now, I would argue that the obvious thing an impediment does is perhaps break things. You could understand that if water had to go around a rock, it sort of breaks the rock, the water. The water molecules are forced to separate. There's all kinds of turbulence and consequences of obliging them to change or adapt to the fact that there's something in the way. And so that photons are changed by impediments. They're broken, essentially. And that if they're broken and they're changed in their direction, that you can put broken pieces back together again and regain the photon. So the evidence that really supports this idea is the fact of polarizing filters. For light, the filters don't get hot. The photons aren't destroyed. They're just invisible. They go from being visible, that is unbroken, unbroken, and they're broken, just in a subtle way, having their phase changed and missing elements. And by just breaking off a few fragments, you change the nature of what the photon is. Because photons are a thing, a length of stuff, okay, sort of understood by quantum mechanics to be quanta, clumps of energy, momentum. That's the message being sent, is a message is saying move. That's what photons do. They move electrons, and by moving electrons cause electricity and other effects. And that's the simple explanation versus their complex one. And their incomplete one, and their inaccurate one, and their one that doesn't fit the evidence. They just pretend it does.
The light interference for the Young's double slit. And so
right, so the light doesn't interfere. It just, you break it and you can remake it, or you don't remake it. So it's just constructive reconstruction, or you leave them broken. That's it. No destructive interference. No interference.
What this is, it's, for example, we have a screen with two small little slits a distance d apart, and we shine light on those two slits, and of course those slits are really, really close together. Typically they're within a fraction of a millimeter or a few millimeters apart.
Or a few. Yeah, no, they're not a few. So it's anyway, yeah, a few millimeters ain't gonna work. But anyway, what do I want to say? Not work well anyway. I haven't seen it done with a few millimeters. Anyway, so remember the math he's going to use is the same math they use for the single slit, and all they do is change the meaning of a variable. So the d that he has in his equation, the thickness of the slit, becomes the width of the opening, which is kind of strange. The thickness of the impediment in the double slit. I don't know if I should draw yet or not. Oh, wait.
And when that happens, when you shine light on that, when the light goes through these very small openings, it will diffract on the other side of the...
So that's the part they got right, okay? The idea is that we know it diffracts. Now, they don't explain why it diffracts. Just zero explanation for the cause of light changing its direction. And I would argue the obvious cause would be electrons. That every surface has electrons on the outside, because that's how atoms are made. Atoms have electrons on the outside and protons on the inside. That's how they work. So every surface is electron heavy, and all you can do is change how you can push the electrons in a little bit and change its polarity. But the electrons are still the electrons. They're still on the outside, and you can just change how close they are to the protons. And that when you bring slits together, you're essentially causing that effect in the sense that the electrons don't like each other. They're both pushing into the surface that you're forcing. You're forcing that to happen, essentially. And if all things are left equal, they'll tend to decide to, as soon as you bring them to a certain closeness, they'll have to decide that one side goes positive and one side goes negative, and that just means that one side pushes in further and the other side pushes less, just to balance the protons and the electrons, make them more compatible with each other. All right.
Of the openings, and that's because the wavelength of the light is somewhat proportional to the size of these slits, and so
somewhat proportional doesn't mean much, because yes, you can do it with white light and you'll get rainbow patterns, which just means that the electrons and the different wavelengths of light will reconstruct in different places because of their cycle difference. So this might be worth drawing. Maybe. It's possible. I don't even, it's hard to say whether it's even worth communicating with a human being, because you really don't want to hear about how anything is fixable or anything that's broken. You just none of you want to hear it. So anyway, it's visible enough. So if you thought of it as the frequency being the size of a wheel, you could argue that red light and blue light have a different wheel size. So if you were to think of their being on phase as being a point on that wheel and how much distance it covers, the ground should be even, but whatever, close enough. And so you turn the wheel. You can understand that this little wheel is going to roll more times for one cycle than the big wheel. And that's essentially deciding the difference between these, where the light ends up. So basically where the argument is that the slits are creating diffraction. So that is, the openings are shooting light in all directions, spreading light. So it's just spreading it. And the argument is if it's blue light, the frequency is smaller, so it goes through cycles quicker. And so basically all you're determining here, where you're going to view where they recombine, you could sort of understand that because of the higher frequency, the fact that it's cycling more quickly, that it's going to show up here where the two off phases are going to match. So you're really talking about, when you do a length difference, you're saying, okay, the little bit longer one's a little bit off, a little bit off, a little bit off, a little bit off, and then it's a little more off, a little more off, a little more off, a little more off as I make the distance longer. And I go longer distance, a little more off, a little more off, a little more off, and now I've almost drawn it backwards, but it doesn't really matter. You get the idea that eventually I will be one complete phase off. So eventually the two wheels will turn, the longer distance one, the one traveling a longer distance, and this one traveling a shorter distance. The two wheels will be in the same position, so to speak, at the same time. They'll be, this one will roll 20 times more, but at this position they'll both line up. And that's basically what you're saying here on the surface, is where do they line up. So there's blue light. If this was white light, let's say, there would be pieces of blue light going to all these locations. But this would be the first location where a beam from here and a beam from here line up, where they've gone through a complete one phase. And it's going to be a sooner that it can do that than this big wheel. The big wheel can't do it as quickly, so the big wheel has to do it here. So the red light, using yellow, but whatever, has to travel. There has to be a bigger difference in the travel length before that one will show up. And so there is red light going here, red photons, but they can't be in phase. They're going to be out of phase. That is, one of them's going to be, in this condition, and one of them's going to be in this condition, and they need to be in this condition. They need to be one whole phase out of phase before they can remake a photon. And remaking the photon just means, again, the photon has been broken. This is missing a piece, one photon, and then the other photon just happens to be missing different pieces. So it has this, this, and this. And so now there's one photon in here. There's the positions make it so there's a whole photon restored because one has the elements that was missing from the other. And to have a photon, you need 5 or 6 or 10. Our human eye needs, they say, between 6 and 9 of these before we can say it's a photon. So if it's missing one of the clumps, again, getting back to the real truth here, they know it's quantized. And yet they just keep pretending that it's not the truth, that what's really happening, even if you were thinking in terms of wave theory, what's really happening is your wave, okay, is going through and then it stops because it's missing this clump. That's a dead clump, and then it's waving again. And this can't do what a photon needs to do, which is push electrons. And it can't push them enough because the electrons move back because of this missing bit of energy. If you give the electron a chance to move back, then you can't push the electron as far because the electrons are in tension. I mean, this is the reasonable, rational explanation for what's happening. And it's just amazing that on a planet of 7 billion people, granted, most of them haven't heard that there's a reasonable explanation, but they're clearly not looking for one either. And clearly all the people that have heard it don't care. Most. Are uninterested in the fact that, oh yeah, there's a better explanation, and we'd rather just ignore it. And that's all I see happening. So anyway, he just says this stuff as if they've proven it, they know it for some reason, they're absolutely sure it's the correct answer, when they don't really have any reason to believe they have the correct answer.
Therefore, light will just fastest lights go in all different directions, which means that no matter where you look, let's say on a screen at some distance away, maybe a few meters away from these slits, you'll see what we call an interference pattern. A pattern where you see sections where there's bright light, and then no light, and then bright light, and no light, and bright light, and no light.
Right, so if you do it with white light, full color spectrum, then you'll get blue, you'll get lots of different patterns on top of each other. The blue light will all line up, the red lights will all line up. But that pattern isn't dictated by anything. It doesn't mean anything in the whole process. The little bits that are getting ripped off of the photons, it doesn't matter when it's going through the slits. The red light doesn't do anything different than the blue light. They're all doing exactly the same thing. There's just little quantas. The little quantas are getting all mixed up. And all you're doing is remaking the photons by putting them back in phase. If you put them back in phase, the pieces can be put together. 2 broken photons can be turned into a new photon. A reconstructed photon that came from 2 different places. It's made of bits that came from one slit and bits that came from another slit. And again, they're hitting all the locations. They're hitting the entire screen. But only at specific locations are they back in phase. And they have to be in phase to be seen. Having just the parts is only half of reconstruction. You also have to have the parts in the right phase.
And so we see these, what we call these fringes or interference patterns. And
the right distance between them, right? I mean, the idea is that you're just knocking bits around. You're just taking chunks off of a blue photon, red photon, it doesn't matter. As long as you can get the phase back, it doesn't matter. So theoretically, you could actually take a piece of a blue one and put it into a red one if it just turns out that they're on phase. But why make it that complicated? So there's two parts to the equation. There's having the pieces, and then it's having the pieces in the right location. So in this location, the pieces can't make a photon. So you could have two pieces coming from different places, but if they're out of phase, they're not going to be able to make a photon. So they have to recombine where they align up and they're hitting the surface at the same time to be able to make the photon. And the idea is this one was missing this one, and this one was missing this one, and now you have the frequency back, which is what you really need, is the frequency. So you have to have the parts and you have to have the frequency. In the end, you have to make the frequency, and the only way you can make the frequency is to have parts and to have the parts in the right order.
The reason why they occur is because at some points you'll have a situation where the light will come together like this in a single location, and you can see, of course, that there will be a path length difference at that particular location, and therefore you'll either have a constructive or destructive interference. I didn't quite hit it right, but let's say we have maybe another situation where the light goes like this and the light goes like this, and again you can see that there'll be path length differences on different locations.
So again, it really doesn't have anything to do with the points. It's the light's going everywhere. There's bits hitting here from here, and then there's bits hitting there from there. But the point is only at certain locations have the wheels of the two photons rotated so they both have the little line that's on the wheel. They're both pointing at 12 o'clock, and so the two different paths, and yet they roll the right number of times for them both to hit the surface when they're at their 12 o'clock position. So it's just where they line up that they become visible photons. There's just as much energy in those dark spots. The same amount of energy is hitting the dark spots. The energy is just hitting in a form we can't see.
Locations on the screen away from the slits. And of course, if the path length difference is exactly equal to a wavelength or two wavelengths or three wavelengths, then you'll have constructed.
This is part of the reason why the pattern doesn't look like the math says it should. It really should have much bigger dark spaces, essentially. And if you look at the pattern, it's always the bright spots are much larger than the dark spots, especially when you get into Newton's rings. You have a clear, just glaringly obvious, clearly on and tiny little bit of off, and clearly on, tiny little bit of off. And the math says it should be a gradual. From the darkest dark to the lightest light should be a very gradual line.
Interference. If the path length difference is equal to half a wavelength or 1.5 or 2.5 wavelengths, then you'll have destructive interference. And so that's why we have these patterns.
So again, no interference. You either remake the photon, you either have the right pieces and put them back in the right order, or you don't. And where you do, you see light, and where the roll rates are different from the two sources, you don't put them back together.
What we're going to learn today is how to calculate the path length difference in such a way that we'll get these various interference patterns, and how far apart they are, and how wide they are, and so forth. All right, now.
Yeah, and so all of that doesn't fit the experimental results. They'll never do the experiment where they show how the experimental results duplicate this math, because it doesn't. The math is a generalization. It really doesn't tell you the truth. It's only half truth or quarter truth, but it's not the whole truth. Clearly doesn't fit. You must resubmit.
The spot directly across from the slits, you can see that those rays would travel the exact same distance. So obviously, when we get to this point right here, you're going to see constructive interference, and this is called the central maximum.
So again, there's no constructive interference. You're obviously going to be able to, you have the phase for all, like if you had white light all of them would have the same phase, they'd have the same roll rate, they roll the same distance, so they'd all be 12 o'clock. So your phase problem is solved in the central location, and all you have to do now is have the right pieces. And you know, that's going to be some of the light isn't even going to get broken, so theoretically it goes right through the slits and it'll end up in the middle. But anyway, there's also going to be constructive recreation of photons that were broken. That's why it's much brighter.
And then we have the first dark spots where light will completely destructively interfere, so you'll see nothing at all. And then you'll see the first bright spots away from the central maximum, so that would be the first max, and that would then be the second max.
So again, this is just the roll rate. So if you had two lengths of travel time, there's a certain amount that you must make the increase. So if you're going to have an increase in the two lengths, so you have a roll rate if something's rolling, and you're going to roll on a length. For you to be able to start another one here and have it roll the extras matching, there's an automatic amount of extra distance you have to go for you to synchronize those two rolls, the lengths, so they match again. Let's see how to put it. Yeah, I don't know how to say it, but this is a set distance. You can't avoid having to add this much extra each time you want to have a phase shift. So each time you want to have a phase where they line up again, you know, except it's a roll behind, this is a set amount of distance that you have to travel extra to be able to be back at 12 o'clock when this one's at 12 o'clock. Yeah. So again, the frequency of the light doesn't mean anything going into the experiment. It doesn't matter at the slits. Nothing different happens to the blue light that happens to the red light. Exactly the same thing happens. The only thing that changes is the fact that to put them back together again, there's rules about how much extra distance you have to travel to be back on phase. And that's what decides where you'll see the blue bands versus the red bands.
And that would be the third max and so forth. So these are the interference fringes, and of course you have the first dark spot, the second dark spot, the third dark spot. So let's hear this is the first dark spot, or completely destructive interference occurs there. There's the second dark spot, and so forth. And then the question would be, well, how far away from the central maximum do these things occur? We have the dark spots and the bright spots, the bright fringes. And we usually call this distance y. We call the distance across to the screen, call anything, and let's call it L. And then the distance between the two slits is d. And of course, we need to know the wavelength of the light that we shine on it. So that's also important to know. So we need to know the wavelength lambda. And then how do we find these bright?
So obviously distance just has to do with how big they're going to be. You know, you're just projecting it on a screen. The distance from the screen is just going to say how large is the image going to be. You know, the further away you are, the bigger the image is. You know, this just, you know, the only variable that really matters is how narrow or how big the impediment is, because that'll tell you what the electrons are going to do, how compressible the electrons are, and you know, how they're going to affect the beam. How much they're the one causing, the electrons are causing the effect of the deflection. Okay, so the diffraction of the light, the spreading of the light, is being caused by the electrons. I've already sort of been over this, but the electrons are in tension. So when you hit one, it doesn't move straight. So the electron is tied to a surface with energy, okay, of the atom. And so when the photon hits it, the electron doesn't move straight. It moves a curved path, or it moves a path because it can't go into this other electron that's here. It moves perhaps this direction, and when it does that, then it moves back, and when it moves back is when it's releasing the energy of the photon. So that's the reflection at the new point the electron is in, it's reflecting energy from the external universe. It consumed this energy to go here, and it essentially gives it back by making an exchange with the universe, and the universe sends out the bit at this time cycle, and it's the same bit. Again, all energy is the same stuff, whether it's in the form of magnetism or electricity or photons of light or gravity. It's all the same stuff, and the only thing that makes photons distinctive is the fact that they do have a consistent frequency.
Well, to do that, let me make a small modification here. We'll clear this out, put my Y back. And let's say that we want to find the location of the first maximum. Well, the first maximum would be right there. And you can see then that this path is slightly longer than that path. And if we try to figure out how much longer it is, if I draw the perpendicular line from here to there, I can then say that this portion right here would be the extra distance traveled by the second ray compared to the first ray.
So, and again, when he says the first maximum, he's saying the first place where the two cycles are back in phase. And the real point is that one photon, that is one row of quanta, one cycle of waves, is a full cycle ahead of the other one, because the other one had to travel the longer distance, and now it's a cycle behind. But now the little nodes are lined up, so the two waves are now back in alignment and can make a photon. And if they're broken, that is, they're missing pieces, but they're missing different pieces, you can put it back together.
And if this angle here is theta, then this angle here must be theta as well. Makes sense, because this is perpendicular to that, and this is perpendicular to this. So
yeah, I mean, when they go through the electrons, the photon it's just one piece out of the photon for each electron. So something consistent. I hate when I drop chalk. Alright, so what do I do with that piece? Oh, it doesn't matter. So the idea is this is going in, right? Something in a row, and what's happening is because of the fact that they're a little bit out of alignment, different pieces will get knocked off of different ones will hit an electron. So say this one hits an electron. Well, that means this one is now going this way. And the rest of these are still going this way. And then some other element will hit an electron, it might go that way. So you have these individual elements have been broken off. So you still have some of it that's going to get through without hitting any electrons, and some of it will hit electrons. And the pieces that hit are going to meet up at another location where, say, these three survived, and the one coming from over here, he fits this position, and the one coming from over here fits in this position. So as long as the phase is back, you can reconstruct the photon.
those two angles must be equal. And then if this distance d is the hypotenuse of this triangle, I can then say that this extra distance, which is opposite to the angle, can be expressed as the hypotenuse d times the sine of theta. And if the extra distance traveled is equal to 1 lambda, we get to the first maximum.
So that's the thing. You can just measure the actual distance, and if you already know the wavelength of the light, you know how many nanometers the distance has to be. So once you have that number of nanometers, you know you have a wavelength of difference.
Maximum. If the extra distance traveled is equal to 2 lambda, then we get the second maximum. And if the extra distance traveled is equal to 3 lambda, then we get the third maximum, and so forth. And in the very same token, if the extra distance traveled by the second rate compared to the first, and you can see then as for you to go to these next fringes, of course, the angle has to become greater, then theta becomes greater, and as theta...
Right, so all you're doing is changing that amount of distance, and you're changing it from where they're one cycle out of one's traveled a whole cycle more distance. And that's all you're doing, is adding that whole cycle. And if you're too much out of phase, then you change the frequency of the light. And the critical thing is you can't change it in the photon itself. For the photon to work, all of these need to be the same. If it's 500 nanometers of distance, it needs to be 500 nanometers of distance. And this is 480, just won't work. And 520 distance won't work. So that's what decides whether you put the photon back together right. So you have the photon. This one's just here instead. And if I put it here instead, okay, if I move it just a little bit off, it's exactly the same amount of energy hit the surface, but you're going to say there's no photon there. You're not going to be able to see it because it's enough off that it changes this equation where it's got to hit the electron and move it. And the only way to hit it and move it is to prevent it, to hit it in an order that prevents it from springing back, going back before you finish pushing it. So you need to push, 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 push. And if there's missing a push, then the spring springs it back and you lose what you gained and you won't get the electron far enough out of its position. And if you don't get far enough out of its position, you won't create a new photon at the right frequency.
Becomes greater, the extra distance becomes greater as well. So you can see how that works. And so if the extra distance travels equal, let's say, to half a lambda, we get to the first dark spot. And if the extra distance travels equal to 1.5 lambda, we get to the second dark spot, and so forth. And I think you can see the pattern here. All right, so now the question then becomes...
So again, it doesn't have to be 1.5. It can be 1 1/4, 1 7/8. It can be all kinds of numbers that aren't multiples of 1, 2, 3, 4. So anything that's not close enough to a full 1 or a full 2 or a full 3 is going to end up being a non-photon. And it doesn't have to be 1/2 cycle out of phase. It can be any cycle out of phase. Any out of phase is too much out of phase.
How far away from the center maximum are these particular things? Well, as an example, let's say that the wavelength of the light that we're using is 600 nanometers. And let's say that L is equal to...
So this part of the math is pretty reliable because all it's really telling you is what, if you're going to compare the two things, the amount of the change in the distance, you're just measuring the distance, which is what equals a wavelength. How much distance equals a wavelength? And that's all you're really doing here. Nothing sophisticated at all. So yes, this math works and is accurate, but it's so simple that it's not telling you anything.
To 2 meters away, so we put the screen 2 meters away from the slits, and let's say that D in our example is equal to 1.5 millimeters, like so. Then where would we find these dark and bright fringes? Okay, well, let's start with the first one. We want to find the first dark spot. So to find the first dark spot, what is the condition? To find the first dark spot, we have to say that. Yep.
So again, D is just telling you, again, the pressure of the electrons. So the closer you put the two surfaces to each other, the more the electrons are going to behave differently. So if the two surfaces, you could argue, if something's really thin, the electrons on one side and the electrons on the other side don't really want to be pushed into each other much at all, so they're under a lot more tension. If the material is thicker, then there's more room to push the electrons in. So they're under less tension, so they're going to pop out of the surface less. So instead of, when you have a thick impediment, the electrons just pop out a little bit, right? You have a thin impediment, the electrons pop it out a lot, so it spreads the light more. So the smaller the D, whether it's the distance of the two slits coming in from the sides, the closer the two surfaces. The D is really just telling you how far away are the surfaces from each other. They're not telling you how thick is the material or how big is the opening. It's just telling you how far away are the surfaces. And how far away from each other the surfaces are tell you how much pressure the electrons can take, how much they're willing to be moved in.
Extra distance traveled must equal half a wavelength. So the extra distance traveled must equal 1/2 of a wavelength. And so we know that the extra distance traveled is equal to d sine theta, according to our geometry.
So again, it's this half wavelength, has nothing to do with it. It's you're either out of phase or you're in phase. And that's all there is. The half is just saying what's perfectly out of phase. But it doesn't have to be perfectly out of phase to still be out of phase. And therefore non-reconstructible.
Here, so we can then say that d sine theta is equal to lambda over 2. Now, how do we relate sine theta to y and to L? Well, it turns out these are very, very tiny angles. And for very small angles, the sine of theta is equal to the tangent of theta. So we can write d tangent of theta is equal to lambda over 2. And of course, the definition of tangent of theta is opposite over adjacent. So if I draw this line right here, I can see this is the opposite side.
Again, you don't even need the theta if you have the distance. So you could just ignore the angle and just go with what that angle corresponds to in terms of distance, in terms of how much length difference there is between the hypotenuse of it and the straight side. And you can just take a shortcut, and then you don't have to do any of this cosine, sine stuff.
To the angle, this is the adjacent side of the angle, so I can say that tangent of theta can be written as y over L equals lambda over 2. And you say, well, wait a minute, this line right here doesn't quite go directly across the central maximum, and that's an aberration of the drawing. These slits are actually really, really, really close together. So the distance from one slit to the other is so minute that basically they're directly across from the central maximum. The reason why it doesn't look that way here is because I drew it a lot bigger, so it's easier to see. But in essence, it is very close to be.
Right. I mean, the light going through the middle of the slits and getting, say, uninterrupted or disturbed by electrons is really hitting a tiny point on the target. The straight line path is just so close to the center that you wouldn't quibble.
Being accurate. Okay, at that time, we're going to find y, so we solve this equation for y, so we have y is equal to lambda times L divided by 2 times d. Putting the L up here, putting the d down there, solving for y, and then plug in the right numbers. And let's see here, in this case, we have y is equal to lambda, which is 600 nanometers, that's 600 times 10 to the minus 9 meters. That's the wavelength of visible light. The length, the distance to the screen, was 2 meters. Then we divided by 2 times d, the distance between the two slits, which is 1.5 millimeters, which is 0.0015 meters.
So I mean, all this.
And what is that distance equal to? So
I mean, all this just for the simple pointing out that you have to roll a whole extra wavelength to have a new position where you'll have the opportunity to put pieces back together because they'll be on phase.
600 e to the 9 minus times 2 divided by 2 divided by 0.0015 equals 4 times 10 to the minus 4. 4 times 10 to the minus 4 meters, which is equal to 0.4 millimeters. So 0.4 millimeters from the central maximum, we find our first dark spot. All right, now next, we're
0.4, so 0.4 of a millimeter, which is really small, at 2 meters. Must have done something wrong in there somewhere. Yeah, that's pretty small. But anyway.
Going to find the first bright spot. So
should have been like a centimeter
maximum.
At least.
And then the conditions to have a first maximum, that means that the extra distance traveled will now be equal to a whole wavelength right here. If it's equal to whole wavelength, we get our first maximum. And of course, our first maximum will always be equal to d sine theta. Of course, we need a bigger, slightly bigger angle theta in order to get to that first maximum. So the conditions is...
So he said a half millimeter from the center. So that's where the center starts to be important. When you're saying it's a half a millimeter, then how big your slits are starts to be relevant because they're only a millimeter. So, yeah, so that's a little wacky. So he was doing the dark spot first. All right, let's just zoom through this because we don't need dark spot stuff. I mean, this is all, the standard crap. And again, there's nothing I'm disputing about the calculation of where you will have the beams back on phase. Where they'll be back on phase is a pretty reliable calculation. The fact of what they think the theory is, that these photons are interfering with each other or banging into each other as wave functions or some other thing, that's not happening.
For the first maximum, that the extra distance traveled is equal to a whole wavelength, and the extra distance traveled is equal to d sine theta, so d sine theta is equal to lambda, and then again we do the same thing. Sine theta is approximately equal to the tangent of theta, which is equal to y over L. So we can say that d times y over L equals lambda, or y is equal to lambda L over d. And then if we plug in the values, lambda again is 600 times 10 to the minus 9 meters. The length, that's the distance to the screen, is equal to 2 meters. And then d, the distance between the two slits, 1.5 millimeters or 0.0015 meters. And the answer then is, I have to look very carefully, notice that it's going to be twice as big as this because we don't have this 2 down here. So it's going to be twice that number. We'll work it on the calculator. We'll get 8 times 10 to the minus 4 meters, which is equal to 0.8 millimeters. So exactly double the distance will get us from the central maximum to the first max across this first dark spot, which is 4/10 of a millimeter away, and this is 8/10 of a millimeter away. Now, what if we want to find the second dark spot? Okay?
Well, he's just doing the same thing, so it's just over and over. But the real point is it's not what their math says it should be. It should gradually go on and then get really, really bright and then gradually turn off. And that doesn't happen with photons. Clearly, what's happening is they're either close enough to phase to put together, and so there's some that are barely close enough. Just the errors of the surface and different things will get you some light, and then it's pretty much all on, because the rest of them are all in phase, the pieces getting put back together, and you get a consistent number of pieces, and you get a pretty solid band of light.
We do the same thing again. We come over here, second dark spot. The conditions to find that, we know that the extra distance has to be 1.5 wavelengths. So here we go, extra distance is equal to 1.5 lambda, which is equal to 3 over 2 lambda. And so extra distance traveled again, that's going to be the d sine theta.
It's always handy is
and then, of course, sine of theta is the same
how
as
much
tangent
you're
of theta,
changing
which is the same
from
as y over L. So we can say that d times y.
The distance difference in the length corresponds to amount of distance on the surface depending on how far away you are. So the further away you are, the more distance you're adding to that little distance. It's just a proportion. And so all of this math just to do a proportional relationship, that the relationship of the hypotenuse to the whatever you want to call it, the side, is a proportion. So all you're doing is changing the place that you're measuring that proportion.
Y over L is equal to 3. Oop, that's a terrible looking 3. Let me correct that. So 3 over 2 lambda, or no, we're not looking for d, we're looking for lambda, or in this case, we're looking for y. Y is equal to 3 lambda L over 2d. And then, of course, you can see that that's going to be 3 times as much as this. When we plug in the numbers, we're going to get 1.2 millimeter. Okay, then if we want to find the second bright spot, or the second maximum,
too redundant, really.
The condition for that is going to be that the extra distance traveled.
Not interesting at all.
That the spacing seems to be fair. The extra distance traveled equal to 3/2 lambda. To find the second bright spot, we send the extra distance traveled equal to 2 lambda, and so forth. So the general pattern is to find the bright spot, and so to find the...
It's always the same, and you can get into all these arguments. If you really want to do the experiment correctly, though, you put it on a curved surface, because frankly the diffraction is a curve, and if you want the lengths to be proportional, that is, they should be exact duplicates of each other. The angle is always the same, and the distance will change because you're projecting it onto a flat surface, so the locations are going to be off if you try to do your math with a flat surface. I mean, the math is going to tell you where the locations would be if the surface was equidistant from the slits.
Maxima, or bright spots, you simply set the extra distance traveled equal to an integer number times a wavelength. 1 lambda, 2 lambda, 3 lambda to find the first, second, third bright spot. If you want to find the dark spots away from the central maximum, you find the extra distance traveled equal to 1/2 lambda, 1.5 lambda, 2.5 lambda, and so forth. And by the way, it also works in the other direction. If you start looking in this direction, then of course the top beam will travel farther than the bottom beam, and again the extra distance traveled will be equal to either a full wavelength, 2 wavelengths, 3 wavelengths to find the bright spots, and it'll be equal to 1.5, 1/2, 1.5, 2.5, 3.5 wavelengths to find the dark spots looking down as well. And that's how you find the interference fringes.
So again, the phase will only be recreated in certain locations, and that's all he's saying. And the truth is that the energy, the pieces of photon, went to all the locations, and it's just in the certain locations that they're back in phase and they can be reconstructed into a photon. That's it. So anyway, probably enough. Maybe we'll do some more interferometer later. Lots of curious things. I haven't quite got it all down yet, but we're getting closer and closer to the right answer instead of their wrong answer that they've been selling for decades. And it's just plain, it doesn't fit their evidence well, and they should just admit it. And their theory of wave-particle duality and particle interference, however you want to call it, wave interference, isn't the explanation. They're not waving in a medium. The photons are real things, and they don't interact with each other. They interact with matter, like all energy. So, enough said, I think. So till the next time and such. I might as well play the very end.
We call them. These are fringes of light and dark that we find because of the interference pattern of light after light.
No, the recombining of photon. After we broke photons, we remade them again. That's all it's happening. Break them and then remake them.
Goes through two slits called Young's double slit, and then because of that fraction, forms these patterns on the screen away from these slits. And that's how you find the bright and dark spots of the interference pattern.
And all you really need to understand was the Pythagorean part of it. You just have to understand that the length of the line that the two circles have to roll has to be increments of a wavelength, as the rolls have to meet at a point. 12 o'clock. All the clocks have to be 12 o'clock. All right. Till the next time. In this rather depressing process of, just arguing stuff you can see it, you can understand it, right? So 364 likes, 5 dislikes for an arrogant statement, just saying this is the way it is, when they can't really defend their theory, and every bit of their fundamental physics to define what's happening is dependent on all kinds of notions of wave interference and all kinds of interpretations, Copenhagen, many worlds, all kinds of wacky, extraordinary notions. New universes are created because a photon went through a slit. Come on. Jeez. I mean, people are just belligerently ignorant. I mean, and you just belligerently lack integrity. I mean, not to be able to admit that, yes, their evidence for their mechanical theory is weak, like non-existent. Their own explanations don't even fit their evidence, and they have to tell you silly stories about, well, we put detectors on and the detectors caused all kinds of effects, and none of that ever happened. They can't tell the story honestly. It's just not worth paying attention to. So anyway, till the next time and such. Need a cup of coffee.